So let me now change my hat and take the hat of chairman. I'm super happy. I'm super happy to chair this session, to introduce Jim Hamilton. Again, as yesterday, I think to this crowd it's not necessary to introduce Jim in detail, but on a personal note, Jim he is my source of inspiration in terms of everything that relate to Markov switching stuff. So I started my career with this, and the first book that I bought was, of course, time series analysis. And at home I have something which is basically has no value, that is a book, the time series analysis with a word from Jim. So that's something that very likely no value today. So, Jim, I'm very, 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 very happy. Your work on Markov switching stuff, time series analysis, this is something that we like all a lot, including all the other work. But I would like to say that also for us, what is important is that you are not only an academic, you are involved in policy, so you like to do assessment of what's going on in the world, in particular in the US, and I would like to refer to the blog that you have with Mandy Chin, Econ Browser. If you don't know this blog, please have a look. That's really fantastic, and I read the post by Jim on each time you have a publication of US GDP, you can understand what's going on if you have a look at Econ Browser. So, Jim, my pleasure to have you here, and the floor is yours.
Thank you, Lauren, for those kind words and for the introduction and the invitation to join this. Great papers presented here. It's an honor to be part of this and a delight to be in Montreal this time of year. This is a joint paper with Christiane Baumeister. And the origin of the paper was I heard this idea from Gabay and Cohen that they referred to as granular instrumental variables. And the suggestion was you could take an arithmetic average of the oil produced by every country in the world, take the difference between that and the total production of crude oil, which is basically a volume-weighted average, and the difference between those two could be a valid instrument for purposes of estimating a demand elasticity. And when I first heard that, I said, how can that work? They motivated in a way that was a little differently from how I would think about oil markets. And so I tried to write down what to me was a little more traditional model and found that under certain assumptions, yes, you could motivate that. There we go. You could come up with that idea. But in fact, when you wrote down those assumptions, you could estimate everything. What I'm told now is maybe the foundational model. You simultaneously estimated every individual elasticity, how they interact, equilibrium, what's going on. And furthermore, it's eminently testable, these assumptions. In our data, it turns out to be rejected, unfortunately. But there's a way to generalize that approach. And so that's what we do in the paper. We're going to provide, to my knowledge, and you can correct me if this is wrong, the first synthesized view. We're going to come up with estimates of each country's individual supply and demand elasticity, how they interact overall. Our estimates aren't going to be that different from estimates people have come up with from a variety of other methods. Maybe that's a little reassuring. But we do come up with some new findings. For example, we emphasize the stabilizing role of inventories. We find inventories tend to go down when there's a temporary price increase, which helps stabilize markets. In fact, that's a very big factor right now, I think, in why the developments in the Middle East have had less of a consequence than they otherwise might have. So in terms of the data we're going to be using, we're going to take monthly data from 1973 through 2023. There's one question, what do you do with COVID when the oil price went negative? I actually have a new book coming out. I have a chapter on what to do with COVID. One of the options is throw it out. And Actually, that's what we do in this paper, just not to deal with that thing of COVID as being a totally different regime. And so we use pre-COVID and post-COVID data. So QIT is going to be the growth rate of oil production from country I in month T. SQI is the share of country I, the average share of country I in global production. And so the volume-weighted growth rates is approximately the growth rate of total world production. And so we'll suppose there are n different producing countries. Now, in our empirical analysis, we're going to take n equal to 4, the 3 biggest historical oil producers, which are the US, Saudi Arabia, Russia, and we'll put the rest of the world into a single category. I could show you the algebra, and everything would be fine, how we could estimate this system with arbitrarily large n. The trouble is it has too many parameters. We've set this up in a very richly parameterized way, and if you wanted to use more than 4 or 5 countries with this approach, you'd need some kind of regularization. Personally, Christiane and I would opt for using regularizing using informative Bayesian priors. I think that's the way to do this. We didn't want to do that in this paper because we've gotten some flack in some other work for using informative Bayesian priors. And also, methodologically, it was much cleaner if you let me do everything with unrestricted, uninformed, full information maximum likelihood. We know that that's the efficient way to use this identifying information, and that helps us to explain why this is a better, statistically, more efficient estimator than what we call plain vanilla granular IV. So it is important that the n countries account for all of the world production. So our category 4 is just the rest of the world. And JT is the growth rate of country J consumption. These don't have to be the same countries as the producing countries. We have M of these. In our analysis, we use M also equal to 4, but you could have M a different number from N. We take the 4 biggest oil consumers. The US historically was both the biggest producer and biggest consumer, Japan, Europe, and again, the rest of the world. So that's our data. And the structural model we're interested in is how does country I production respond to the world price of oil? And phi QI is the short-run elasticity of supply in country I. And a key part of what makes this work is the assumption that it's a global oil market. There's a world price of oil P. Every country is responding to that same global signal, although perhaps in a different way with a different elasticity. Now, I know there are differences, Brent and WTI and all that. I think those are usually secondary compared to the fact that if oil price goes up anywhere in the world, it goes up everywhere, and that's the essential thing our model assumes. So we've got a contemporaneous response, and then we've got lags. Here's where we get very profligate with parameters. We include 12 lags of the production of every country, and 12 lags of the consumption of every country, and 12 lags of the world price of oil. That's all included in this XT minus 1 to allow for various kinds of interactions. And then there's a supply shock for a country I, QIT. So, for example, if country I has some monopoly power, set the marginal revenue equal to marginal cost, you can derive an equation like this form where the elasticity in that case turns out to be the elasticity of marginal cost with respect to the quantity produced. And these lags are in part coming from serial correlation in shocks to marginal cost of production. You can also put it into a forward-looking model if you're willing to take a Minnesota-type view that the most important variables for forecasting future price and future marginal cost are the current price and marginal cost. You can also derive an equation like this. I'm going to take it as a primitive, and as I say, we're interested in the short-run elasticity phi QI. Analogously, for country J's consumption, we've got a short-run elasticity of demand, phi CJ. And in our data, global production does not equal global consumption. I think that's something you're going to find in every data set, whatever it is, if it's assembled from different sources. Production doesn't equal consumption. Partly that's because of inventories. We don't have a good direct measure of world inventories. There's something implicit in this difference. Partly it's because of some definitional differences, and partly measurement error. We're going to summarize all that in this equation we'll think of as an inventory demand equation. Inventory demand is the difference between world production as measured and world consumption. We allow there to be various dynamic factors in that and allow that to respond also to the contemporaneous price. So phi v is the response of inventory demand to the price. And it also includes measurement error. Now, we originally formulated this. We actually had measurement error in everything, and you can do that too. It's a little more complicated to explain, and we found the empirical estimates are basically the same if we just put all the measurement error into this inventory demand equation. And so that's the way I'm going to describe it. So here's the basic structural model. We have quantity produced from n different countries. We have quantity consumed for m different countries. And we've got the world equilibrium condition that any gap between those is imputed to changes in inventories, which are also responding to the price. And you can write that out as a vector system. Let me collect all the data in this vector yt, which actually has 9 variables in it. It's a 9-variable system. It has the 4 production numbers. It has the 4 consumption numbers and the world price. And then there are these structural shocks, which are the shock to production, the supply shock, marginal cost shock, if you take that story for country I, the demand shocks, UCT, and the inventory demand shock, measurement error. And so you write that out, and you say, oh, it's just another vector autoregression, which it is. It's a vector autoregression of this 9 variables in YT on 12 of their own legs in a constant term. And there's a particular structure on that matrix of contemporaneous coefficients. Some of the elements of that matrix we know are these supply shares and demand shares, those observed data. A part of those elements are these supply and demand elasticities that we're interested in. But the logic of that structural model is there are these exogenous shocks to marginal cost of production, for example, and those interact through this equilibrium system of equations to determine endogenously what the price is going to be, what the individual production of each country is going to be in response to that constellation of shocks. And so I mentioned granular IV, and I mentioned Gabay and Koyen's claim that you could look at the difference between the arithmetic average, just take 1 over n, the production of each country in the world, and add that up, and take the difference between that and a volume-weighted average, where you're using these shares in production for the weights, and that could be an instrument for estimating elasticity. Now, this is the way they set it up, where there's a like time-fixed effects, for example, for consumption demand, and that's not actually what a typical global model looks like. That's not a feature of this model I wrote down. The model I just wrote down cannot be written in this form. What's going on in the aggregate is much more complicated than can be summarized with a single vector, single vector. But it turns out that you could motivate granular IV and generalizations of it in this example if you supposed, as we typically do, that supply shocks, these UQT, are uncorrelated with demand shocks. And of course, if you just had one country, you can't do it. That's the canonical textbook example. But if there are more than one producing country and more than one consuming country, you've got this whole m by n vector of zeros, which are restrictions on the potential interaction of these unobserved structural shocks. And suppose just to give a simple example, you further said, well, there's a common supply elasticity, a scalar phi q. Every country has the same supply elasticity, and a common demand elasticity, the scalar phi c. Well, why would something like granular IV work under those assumptions? Uncorrelated structural shocks and a common elasticity. Well, we can write down under those assumptions this vector of quantities produced by each country, QT 4x1 vector of the production in each location, as the scalar phi q times the same price showing up in every equation, plus lags showing up in a different way in each equation. So let me take that equation, vector system, pre-multiply by SQ, which are the shares of each country in production, and also pre-multiply by WQ, where WQ can, for this statement, be any vector whose elements sum to 1, and take the difference between SQ, a volume-weighted average, SQ prime QT, and WQ prime QT, some other way of calculating the average. That difference, when you pre-multiply the vector of 1s there in that first equation by a vector SQ whose elements sum to 1, and subtract WQ whose elements sum to 1, you get 0. And so the price drops out of that system of equations. Once you look at the difference between, for example, volume-weighted and arithmetic average, the price drops out. And the price, under these assumptions of uncorrelated shocks, was the source of endogeneity concerns. So if we were to take what would be implied for the process, the difference between volume-weighted and some other, say, arithmetic average of production, it would be purely a function of the supply shocks. And if those supply shocks are uncorrelated with demand shocks, you can use them as an instrument to estimate the demand curve. It's a valid instrument because they're affecting the price and uncorrelated with the error in those equations. So that's one simple argument for how you can come up with something like granular IV in a setting like this. They motivated it a different way. To me, that's kind of a more natural way of thinking about what this is about. Now, you could also, same kind of algebra, you could say I can estimate the supply elasticity from a regression of, say, some weighted average of quantities produced on the price and lags of stuff using a difference between the volume-weighted consumption and, say, the arithmetic-weighted consumption as an instrument. Same kind of logic. Now, you can also think about that system a more conventional way. Rather than say, okay, I want to find an instrument for something, you just write it down. If you suppose that the demand shocks are uncorrelated with supply shocks, you have this block of zeros in the 2-1 block of this matrix. So this is a 9x9 variance-covariance matrix. DQ is a 4x4 matrix. That can be unrestricted. We're not saying anything about potential correlations between the supply shocks for different countries. We're just saying the supply shocks are uncorrelated with the demand shocks and uncorrelated with the inventory demand shocks, the 3-1 block there. And so you got a system with restrictions on A, the impact, the contemporaneous coefficients, with restrictions on D, these covariances between the structural shocks, and you can think about maximum likelihood estimation. Well, it turns out maximum likelihood estimation for that system can be summarized in terms of some reduced form parameters. Pi hat is just the vector of OLS regression coefficients when you regress each of these variables in Y on 12 lags of everything. You get this pi hat. And epsilon hat are just forecast errors for each of those 9 variables in the VAR. So those are both observable objects. I can estimate them without a model. And there's also an implied error in forecasting implied inventories, which is just a volume-weighted difference between the error predicting production and the error predicting consumption. So you can write down that likelihood function. you can differentiate it to find the first order conditions for full information maximum likelihood. And here they are. I'm just telling you, when you do the math, you come up with these equations. But I wanted to spend a little time with these equations. I know these are even uglier than the things Mark put up yesterday. He said, oh, that's ugly. I want to spend a little time talking about these equations because I think they're very intuitive and they explain how this whole thing works. But I want to emphasize these didn't come from intuition. They came from math, from finding the conditions for FIML. So what is it? This common consumption elasticity has this expression, and that's kind of like an IV estimate of some kind of, an IV regression of some kind of consumption, a C with a tilde, on some kind of price, epsilon hat P, which is the error you'd make predicting the global oil price, where there's an instrument, Z tilde CT, some kind of instrument. It's an IV regression. Now, this is often the case. FIML, if you look at it carefully enough, you can see, oh, well, that's using IV. And what FIML is doing is it's telling us what is the optimal instrument. Because we know FIML in this example is the best way to use the information. So what is it? So the C tilde turns out to be a weighted average of the error you'd make predicting consumption of each country, where the weights turn out to be, optimal weights, turn out to be weighted inversely by the estimated variance of each consumption structural shock. And we'd estimate that variance covariance matrix D hat C with just the average difference between what the consumption error was, the imputed demand elasticity phi hat C, and the error predicting price. And this instrument, ZCT, this is kind of the main point of that slide, the fourth equation, turns out to have several terms in it. The first term is a difference between the volume-weighted forecast error for production and some other weighted average of production, where FIML also tells you what those other optimal weights are, WQ. Those optimal weights turned out to be inversely related to the supply shock variances. So that first term there in Z tilde CT is like granular IV. But FIML says that's not the only thing you should be doing here. That's just one source of information, and it's a valid source of information for the reason I just sketched. Another thing you want to look at, according to FIML, is the imputed demand shocks, where there's a certain weighted average of, the imputed, for this is for estimating consumption. You want to look at the imputed supply shocks, the difference between a volume-weighted production Q tilde and subtract off the supply elasticity times the error predicting prices. And of course, we're saying under the assumptions I wrote down, that block diagonal D matrix, that the consumption shocks are uncorrelated with the demand shocks. So that's useful information. That's also a valid instrument. It's also something that affects the price and is valid. And furthermore, you want to use the imputed inventory demand shock. So that's what FIML does. And then there are analogous conditions for the other parameters. Now, I gave you a closed form expression for FIML, at least for the first order conditions, but you can't actually solve that system because to calculate my instruments, I needed to know D hat C and D hat Q, but to get those, I needed the result from the IV estimation. So, but it does suggest an iterated procedure as one kind of nice algorithm, again, for getting some intuition of what FIML is doing. An integrated procedure, which is, you can start with some estimate of, say, the start with some estimate of the demand elasticity, and you could get this, for example, with plain vanilla granular IV. You get an initial estimate of phi hat C from that. Well, now that I've got that, I can go ahead and calculate the variance matrix for the consumption shocks, and I can use that in the next step to reweight stuff and get what would be, according to Fimmel, the optimal weights, and iterate in this procedure. Old-timers here recognize that as iterated three-stage least squares, which is a constructive algorithm for calculating the maximum likelihood estimates. So let me just show you for our data set what that amounts to. And I'm going to compare in the first column here what I call in plain vanilla granular IV, which just uses this difference between the volume-weighted production, in other words, global production, and an arithmetic-weighted production as an instrument for estimating the demand elasticity. Step one of iterated three-stage least squares and stopping there. And so you get an estimate of the short-run elasticity of demand is like negative 0.1, which is kind of a plausible number. That's kind of the number people think it might be. But trouble is there's a very big standard error. In fact, it's basically a useless estimate, 0.25. So yeah, it works. It's not great. On the other hand, if you look at Fimmel, the system from iterating on all these systems, not just stopping with granular IV, you get actually a pretty similar estimate, negative 0.13, but it's much more accurately estimated. Why is it much more accurately estimated? Because we used much more information. We have efficiently used all the information applied by the model and for here. So in terms of supply elasticity, if you use plain vanilla granular IV, you get a crazy estimate of supply elasticity. It's negative at a huge standard error. We know nothing about supply elasticity. And the reason is that the difference between volume-weighted consumption and arithmetic average consumption is pretty small. There's not much variance in that. And so it's a lousy instrument, and so you can get lousy estimates if you use that. On the other hand, since we got a pretty good idea about the demand elasticity, once we start using that to improve our estimate of supply elasticity, we get something that's more reasonable, again, a kind of number like people might think, 0.05, the short-run supply elasticity, and it's estimated much, much more accurately. And also we get out of this an estimate of the inventory demand elasticity, which is negative, and that says when the price goes up temporarily, inventories are drawn down. Inventories are drawn down in response to a temporary disturbance in the market, and this is a stabilizing role, according to these estimates. Inventories play a stabilizing role. At one point, there was a lot of debate about inventory speculation being something that made oil markets crazy. Well, according to our estimate, that's not true. Historically, on average, it's been a stabilizing factor. Now, this is full information maximum likelihood. You can test that, likelihood ratio there. It's heavily over-identified, that model that I wrote down. Okay, I said the elasticities are all the same, all these things are zero. It's got actually 21 over-identifying restrictions, and unfortunately it's rejected. Nice model, nice story, inconsistent with the data. And it's not just because we were assuming there that the elasticities are the same. You can relax that even with different elasticities. And the reason is, in terms of the data, if you look at the covariance between errors in predicting the quantity and errors in predicting the quantity produced and the errors in predicting the quantity consumed, the model says there should be a single vector phi q that can account for all those correlations and a single vector phi c, and it turns out that's inconsistent with the data. But, and basically that assumption that I said is kind of our standard thing, supply shocks don't correlate with demand shocks, that's inconsistent with the data and with the model I showed you. So what can you do? Well, what we propose is to think about a factor structure to these demand shocks and supply shocks, and suppose there's a factor in common. There's something, global activity or something, that's common to both supply and demand shocks, and also maybe a single factor in the separate production shocks and a single factor in the separate demand shocks. And that turns out to be consistent with the data. And so that's the model we're going to use. So it looks like this. Each country is going to have its own supply elasticity, its own demand elasticity, and we're taking out those zeros in the 2-1 block of the covariance matrix for the structural shocks, and we're replacing it with a factor structure that there's just a single vector of loadings on the common, say, economic activity factor in consumption HC and a single vector of loadings of production on that same vector HQ. So you describe that with it's a rank 1 matrix. And similarly, reducing somewhat what the generality allowed for how production shocks can be correlated. Sigma Q here is a diagonal matrix, and apart from that, there's a single factor accounting for, actually, I guess we restricted this. We found you don't need a factor for production, but we do have a single factor gamma C for consumption in the 2-2 block there. And so that's something, that's still an over-identified model. You got 16 over-identifying restrictions, and you fail to reject the null hypothesis that all those assumptions are the same. So it's like structural VARs, except that it delivers lots of testable implications. There were lots of ways this could go wrong, and I'm giving you a framework here that's consistent with everything we observed. So that's what our estimates are based on. And so here they are. These are now the FIML estimates for our favored model, which allows every country to have its own supply elasticity, its own demand elasticity, and which has a factor structure on how these structural disturbances are related. And those are our estimates. Short-run U.S. supply elasticity is 0.02. Short-run Saudi supply elasticity is 0.25. So historically, Saudi Arabia was a key stabilizing factor in the world oil market. That when something goes on to raise the price, Saudi Arabia would respond within the month by a measurable amount. And so all these estimates are kind of consistent with what people thought before our paper. They're the ones you arrive at from this system. And there's also, not only do we have the individual supply elasticities, we have an implied global supply elasticity, which according to the equilibrium model, you calculate just by multiplying each individual country's supply elasticity by the share of that country in world production. And so we get a global supply elasticity of oil of like 0.07 and global elasticity of demand of negative 0.11. So again, actually those are similar to, in fact, the restricted FIML, which I kind of showed you in detail where those come from. But the nice thing about these estimates, even though they're a little harder to get, they're consistent with all the data. So okay, I want to skip things. I don't want to get too far behind. So one of the things we can do, we now have a structural model. The point of having a structural model is you can do counterfactual scenarios. And so let me give you an example of that. We get directly from the likelihood function a short-run supply elasticity and a short-run demand elasticity, which are the answer to the question, suppose the price goes up now, what's the response within the month? People are also sometimes interested in the long-run demand elasticity or a long-run supply elasticity. Now, what do you mean by a long-run demand elasticity? Well, you have to spell it out, but once you spell it out, we can calculate what the answer to that is, according to our model. One way you can spell it out is to say, well, what would happen if the world price went up and stayed up, and country I responded, but nobody else did? It's a counterfactual scenario, but it's one interpretation of what you'd mean by the long-run U.S. supply elasticity. There are other things you could mean, like an impulse response function. Okay, everybody responds, what happens? I think this is closer to the usual concept of what a long-run elasticity would be. And so here are the estimates we got. The longer run elasticities are much higher than the shorter run elasticities. You give us a year to respond, you're going to see a bigger response of consumption and production. Now, the estimates of the longer run stuff are not as accurate. As I say, we've estimated a lot of parameters here, and there's big standard errors on most of these things. You still get some significant findings. For example, the Saudi response, actually 10 times as much response if you give them a year as you get within the month. And that number, for example, is statistically significantly different from 0. So that's one example of a counterfactual scenario you can look at. Another one, which we chose partly because we started this paper a while ago, and Christiana thinks we should update this with something with Iran, but this is the example I have to show you, which is what would happen if there were a 50% cut in Russian production, which, you know, still could happen. Who knows how this event with Ukraine are going to end up. And now, as I say, historically, inventory adjustments have been a key factor in how the world would respond to something like that. However, so we're going to look at this counterfactual scenario. Suppose there's a 50% cut and it is maintained for 6 months. Okay, that's a big cut to world production. There's not enough inventories to do that. And so we can do a counterfactual, which is to say, let's impose that you can't deal with any of that production cut from running down your inventories. So that's the counterfactual. We say Russian production falls by 50%, stays down by 50% for 6 months. There cannot be any responsive inventories. So by construction here, the sum of the decrease in consumption around the world minus the sum of the increase in production from other countries equals 0 by definition of this counterfactual. The world has to cope with it somehow. We don't allow it to be inventories. So somebody's got to either produce more or consume less. And here's the answer to who that somebody is, according to the model here. U.S. Now, everything in the models and elasticities, people who follow the oil market are more inclined to think in terms of like million barrels per day. So I've got the numbers in millions of barrels per day here in that last column. So, for example, we're talking about a cut in production from Russia of 5 million barrels a day, and that goes on for 6 months. And so, according to the model, in terms of impact, what's going to happen? So it's 5 million barrels less this month. What do we do? Well, Saudi makes up some of that. They would increase their production by about 1 million barrels. U.S. Going to be modest. Rest of the world, which also includes OPEC, the way we've set it up, that's another part of the response. The biggest part of the response, though, is consumption is going to have to fall, and the model implies where that comes. A lot of it's from the rest of the world because partly they have a higher estimated elasticity, partly because they are a big factor. So it's an example of the counterfactual questions you could answer. And of course, we get impulse response functions. These are structural impulse response functions. Predicted path of everything under this counterfactual scenario of 50% cut in Russian production. Now, by the way we assume after 6 months, we assume Russia doesn't go back to where they were. We assume that from there, the historical dynamics take over and they're going to start to respond and gradually come back to their equilibrium role. So again, trying to forecast out a year, we've got a lot of stuff in our model and we don't claim to know, which again, I kind of like this aspect of the model. I don't know what's going to happen a year or later. The model doesn't know, but it's got a guess. And the guess is, there's going to be increasing compensation over time from Saudi Arabia, going to be increasing adjustments, but that's the counterfactual scenario. Okay, and just to mention, so all of that was assuming that the parameters were constant over the sample. Of course, our sample went back to 1973. There have been big changes, the shale revolution in the United States. So we were curious to see what would happen if you only used data since 2005, redid the exercise. What you find is that there's more elasticity of the U.S. supply, kind of what people think. Shale is more responsive in the short run. There's actually less response of Saudi Arabia. Saudi Arabia seems to have been playing a less important role in stabilizing world oil prices today than they did 30 years ago. You put them all together, the global supply elasticity, even though there's more response of the U.S., with less response from Saudi Arabia, there's actually less flexibility of the world market in terms of that. We get something pretty similar in terms of inventory adjustment. Okay, so summary is, if you're willing to assume that the structural correlations between supply and demand shocks can be described by a low-order factor structure, which is more general than saying supply shocks are uncorrelated altogether with demand shocks. You can use the correlations among things we observe, namely the correlation between the error you make predicting the price of oil, the error you make predicting each country's production and each country's consumption. You can use those to estimate the full equilibrium model, individual elasticities, aggregate elasticities, how they interact to produce equilibrium, and counterfactual scenarios. Now, I guess I should have added the qualifier. Anytime you start to take something far out of your observed sample, you're on potentially thin ice. So that's maybe another reason those standard errors should be even bigger for that exercise. But I do it to illustrate the kinds of things we can do with this. Now, our view is that the next logical step would be to go ahead and do some regularization, so you could look at a richer system, impose some restrictions on all these lags and stuff. We would recommend Bayesian, informative Bayesian prior, but other people might choose other responses. So let me stop there to see if we have comments or questions from you.
Thanks a lot, Jim, for this super nice presentation. We have time maybe for one or two questions, if any. Yeah.
Hey, thank you very much for the nice presentation. I have two questions. One regarding the shocks you have been studying. Have you considered the shape of the shock? For instance, is it the shape of the shock given a war, or given, for instance, a new discovery in methods of extraction? And the other one has to do with the factor you added to the model in order for the data to fit. I think it's in the slide 27. Maybe you can go deeper in this factor.
Let's see.
Yeah.
Okay. First question about the shape. So we were taking Gaussian, everything to be Gaussian, which has some advantages, that the Gaussian estimates are all these based on OLS regressions and so on. They're all functions of the observed variance covariance matrix. That's really what's being used here. So I think there is a kind of quasi-MLE justification for this, but it's certainly within that caveat that I put in maybe too late about, we're extrapolating far from the historical events, at least in the case of that Russia scenario, and there are plenty of reason to be skeptical of that. Now, as far as the structure of this matrix, so this is it's a block matrix. The upper left 1-1 block, it refers to the presumed variance covariance matrix of the shocks to supply, shocks to marginal cost of production. And so sigma q here is a diagonal matrix. HQ is a n/1 vector. So that upper left matrix is assuming there's a one factor structure to the shocks to supply, and actually that same shock, that same factor is showing up in the 2-1 block through these loadings HC. So there's a single aggregate factor that production loads on with vector HQ, that consumption loads on with a vector HC. That single factor is giving you both a restricted variance-covariance matrix in the upper left and a restricted but non-zero block to the variance-covariance matrix in the 2-1 element. And here and the 2-2 element here is a little more complicated. We've got this loading of consumption on the aggregate factor, HC. We've got sigma C, a diagonal element, and then we've got this vector gamma C, which is a separate factor affecting demand shocks. So we got two factors. This is a two-factor model, basically. There's this one factor that we think of as like economic activity, and there's another factor. I guess I got here are the loadings on the demand factor. It's really kind of a common thing. These gamma C's are all like the same number, pretty much. Each country is responding to something. And insofar as this common, now we also estimated a model where we had like an equivalent to a gamma C up in the upper left block, allow the supply shocks to be correlated. We found that wasn't necessary. We could impose a restriction that there's no more structure there. But basically this all came out of the data. We're looking for a set of conditions under which you could have identification and that you don't reject the model. And you've got to allow for some correlations. You've got to restrict the correlations. Obviously, we had a totally unrestricted matrix here. It's not identified. The identification comes from assumed structure on how these structural shocks might be related to each other. Thank you for inviting me to cover that much more time than I did in the original.
Okay, if there are any other questions, maybe we can put an end to this session. And again, thanks you a lot, Jim, for this very nice presentation. Thank you.